Okay, we're going to start with a review. We are going to review how to convert to polar coordinates, and we're also going to look at some equations. Okay, we are going to start with the unit circle. So rectangular, that's x squared plus y squared equals 1. In polar, let's say we're looking at the whole circle, so we want the inside as well. So I guess this is really less than or equal to 1. In polar, we're defined by r and theta. So in this case, r is between 0 and 1. Theta is between 0 and 2 pi. Instead, we might look at something like this. So this is x equals 1 and x equals 2. If we were looking at this, our r then would be between 1 and 2. Theta would be between 0 and pi. Do we remember the idea between r and theta? R being a radius coming from the origin, theta being the angle of rotation. Okay. You need to remember how to convert. Here are the big ones, the helpful equations. R squared is x squared plus y squared. X is r cosine theta. Y is r sine theta. We are not going to practice converting, because I expect you to already know that, and if not, you can go do some practice on your own. Sound good? That's all the review we're going to do. So, ready to move on? Great. So like I said, the reason we're looking at this is we're specifically going to look at double integrals in polar coordinates. Okay. We're going to start with a figure. So we have our sum surface z. This time z is a function of r and theta, not of x and y. Okay, you know how normally we look at our rectangle r and we map it up to the surface? A rectangle in polar is different than a rectangle in rectangular coordinates. So in this case, this might be our region R. So what we've always done before is we've taken that region R and then we've split it up into pieces, and then we've mapped it up onto, bless you, onto our surface. Okay, so there's a few things that we need to define, a few parameters we need to define on this region. This line here is theta is equal to some value. I'm going to call it alpha. This line here is theta is equal to some value. I'm going to call it beta. This line right here is r. That's a function of theta. This line here is also r, which is a function of theta. Okay, so again, we're still going to be interested in that volume problem. What is the volume between our area R, or our region R, and then the surface? To find that volume, we're still going to use a Riemann sum like we've been doing. Okay, so here's the idea then. Our volume is going to be the limit as n approaches infinity of the sum from k equals 1 to n of f of r of k star, theta of k star, delta a sub k. What does the delta A sub k stand for? Right. So the idea is here we map it up, and do you remember forming the parallelepiped? Okay, and so we're finding the volume of each of those parallelepipeds and we're adding them all up. What does this contribute to the volume? What does this contribute to the volume of the parallelepiped? What does that account for on the parallelepiped? This is the area of the base. What is this? The height. Right? If I plug in r and theta, I'm going to get the height. So this is the area of the base. This is the height of the parallelepiped. Do you remember what those stars mean? Right. Do you remember talking about how you can pick any point in each of those rectangles? Okay. So what this is this is equal to the double integral over the region R of f of r theta dA. Now, here's the big question, though. You guys just told me this is the area of the base. Do you recognize, though, looking at this, that this is not a traditional rectangle? Okay, so the real question is, how do you find the area of a polar rectangle? Because that's going to come into play with our conversion. Okay, so what we're going to do then is we are going to zoom in on this a little bit and do some algebraic work to figure out what the area of a polar rectangle is. Okay, so let's say we have the origin here, and this is our x-axis. We are choosing some point in this rectangle. So that is the point r of k star, theta of k star. This line here is r1 of theta. This one is r2 of theta. This is where theta is alpha. This is where theta is beta. So this piece then is the change in theta. Here to here is the change in r. Okay, so here's what we have then. The change in theta, so that's right here, is just beta minus alpha. Next thing we need to know is how to calculate the area of a sector. Anyone remember that formula? There is an r and a theta in it, yes. Okay, area, what do you think you have to do with the r? Square it. It's 1/2 r squared theta. That's how to find the area of a sector. Okay, so then that delta a sub k, so the area of this rectangle right here is going to be the large sector. Subtract the little sector. With me so far? So large sector being the one that goes all the way out to here, little sector being just the white part. Okay. A few other things. What I'm going to do is I'm going to take a line that goes directly through the middle. The reason I'm going to do that is this little piece now is going to be 1/2 delta r sub k. Okay. So then our delta a sub k large sector minus little sector. So large sector is going to be 1/2 the radius. Okay, using R2 and R1 is not going to be super helpful because then we're going to have both R2 and R1 in there. So instead what we're going to do is we're going to do R of k star. So that'll bring me all the way up to here, and then I just need that little extra red piece. Do you guys agree that that's the radius of the large sector? Okay, so then we have theta minus area of the little sector. If I can use that R of k star again, so again, that takes me up to the red line. This time I need to subtract the red part. Sorry, this doesn't have a star. And then delta theta of k. Okay. You ready to do some squaring? Here's what we get. 1/2 times R of k star squared plus R of k star delta R of k plus 1/4 delta R of k star delta theta of k. There's more. Minus 1/2 R of k star squared minus R of k star delta R of k plus 1/4 delta R of k star times delta theta of k. Okay, we're almost getting there, I promise. So all I did was square this out. Now we got to combine like terms. Things to notice though is that these two are going to cancel out. These two are going to cancel out. So what we get then is the area of a polar rectangle is R of k star, delta R of k, delta theta of k. Okay, here's what we get from that. Volume, which we already said is the double integral over the region R of f of r comma theta dA. Using the Riemann sum, that is the limit as n approaches infinity, from k equals 1 to n, f of r of k star, theta of k star. Instead of delta A sub k, so instead of the area of the base, we're going to put this in. This is the double integral of f of r of theta. Okay, here's the big piece that came from that. Here's what this becomes. This becomes r. This becomes dr. That becomes d theta. And then we're going to go from r1 to r2, and then alpha to beta. Okay. Here's what you need to get from this. For the most part, one thing that's nicer about polar than rectangular, you're always going to integrate with respect to r first. So it's always going to be dr d theta. You're not going to have to figure out which one first. But what's really important is when you convert to polar, you have to include an extra r. So anytime you convert to polar, it's going to be an extra r and then dr d theta. So let's look at an example. We are going to look at the double integral over the region R of sine of theta dA. where R is the region outside the circle, R equals 2, and inside, R equals 2 plus 2 cosine theta in the first quadrant. Okay. In order to figure out our bounds, we're going to have to draw a figure. So let's start with that. R equals 2, you should be fine with. Sorry that my circle isn't amazing. R equals 2 plus 2 cosine theta. Do we know what that looks like? Whew. Okay, so we're going to have some trouble if we don't know what these polar graphs look like. I am going to put a review on Schoology that has some of the most common graphs on there. So take a look at that if you don't remember some of these. How can I approach graphing this if I'm not exactly sure what it looks like? Plug in some points, yeah. It's the one that looks like this. It's not going to be great, sorry. It goes like this. So we need the region outside the circle, but inside the other figure, which is right here. Okay. So then this double integral, it's going to be sine of theta. We're converting to polar, so you have to remember that extra r. And then dr d theta. Bounds on theta here should be pretty easy. What are our bounds on theta? 0 to pi over 2, yeah. In the case of r, if I start at the origin and I go out, I'm always going to get to r equals 2 first. And then I'll get to the other function. So that 2 plus 2 cosine theta. Okay, my concern is the setup. I think you guys should know how to integrate these for the most part because it's pretty similar to rectangular. So my question to you before we start integrating is, are we okay on the setup? Yes? Okay, please do not forget the r because that makes a big difference. Okay, so now we need to integrate. So integrating the r, we get 1/2 r squared from r equals 2 to r equals 2 plus 2 cosine theta. Okay, how are you if I just tell you what it comes out to be once we square and combine like terms? We're okay with that? Okay, becomes 2 times the integral 0 to pi over 2 cosine squared theta sine theta plus 2 sine theta cosine theta, all of that d theta. Here, if you made your u cosine theta, your du then would be negative sine of theta. So this is negative 1/3 cosine cubed of theta. Here, if you make your u sine of theta, your du then would be cosine of theta. So we get plus sine squared of theta. All of it from 0 to pi over 2. Are we okay on that? Yeah, we follow my integrating? Okay, I'm just going to tell you it ends up being 8/3. Questions on that? Okay, most of the time you're not going to be using, the problems are not going to be like this where everything's already in polar. You're going to need to be able to identify when polar is best. So we're going to look at a few examples that start out in rectangular, but that we're going to convert to polar. Okay, we are going to find the volume of the solid that is bounded by z equals 0 and z equals 1 minus x squared minus y squared. Okay, so starting out with a figure, z equals 0 is just a plane. Z equals 1 minus x squared minus y squared, what is that? So what? I just want to know if I were to graph it, what is it going to look like? We're going to have some trouble if we don't remember these graphs. It's what? It's a paraboloid. You got something. Yeah. It's so z equals 1 is going to be the highest value. If you plug in z is 0, you get a circle here. Just remember this, and it goes down. Does that look vaguely familiar at all? Okay. We're being bounded, though, by z equals 0, so we're only looking at the volume of this part. Okay, so our R, then, is where the figure intersects the xy plane. So R is a circle in this case. If we plug in a 0 for z, that's where we get where our figure intersects the xy plane. Okay, so that's our R. So what I want us to do is I want us to first set this up in rectangular. So our volume is going to be a double integral of the surface, so 1 minus x squared minus y squared. I'm going to integrate with respect to y first, it doesn't matter in this case. Bounds for x. Anyone? Bounds for x? Come on, guys. Lowest value for x, highest value for x. Negative 1 to 1. To find the bounds for y, you're going to have to solve for y here. So you'll get negative the square root of 1 minus x squared, positive the square root of 1 minus x squared. Okay, so rectangular, certainly an option. Does this look to be the ideal way to integrate? No. Anytime that your R is a circle or something circular, you're going to want to use polar. So that is one option. You could certainly integrate that if you want to. I'm going to convert to polar instead. So this is 1 minus r squared, like Johnny said. I think it was Johnny a while ago. When you convert to polar, remember the r, and then we have dr d theta. Now we're just looking at the circle. So on this circle, r goes between 0 and 1. Theta goes between 0 and 2 pi. Okay. One thing that is nice about a setup like this, do you all remember that if your integrand is a function of r and a function of theta, you can split up the integral? Okay, maybe you do now that I just told you. So I could split this up to be 0 to 2 pi d theta and 0 to 1 r minus r cubed dr. So that's not always going to be the case. Obviously, with the first example we did, we couldn't do that. This case, you can, though. If you trust me, I'm going to tell you that the answer is pi over 2. Okay. Questions before we keep going? Okay. Are you all okay that I focus more on the setup and not the integrating every time? Because you're going to get that practice in your homework, and it's kind of the same thing over and over. Okay, we have one more concept to talk about, 2 more examples, and then we'll be done with notes for today. Hopefully you remember from before that you can use a double integral to calculate area. What we did before is we took the double integral over the region R of 1 times dA. If I'm switching to polar then, it's still going to be the double integral over the region R. If I switch to polar though, I still have that extra R. So that's nothing new, just remember that you need the extra R. Yeah.
In the previous example, where'd you get the radius going from 0 to 1?
From this circle, the x squared plus y squared equals 1.
Oh, this is just in setup.
Good.
Yeah.
Okay. Anything else? Great. Next example. We are going to use a double integral. To find the area enclosed by one loop of the 4 leaved rows with the equation r equals cosine of 2 theta. So again, you're going to need to know what that looks like. I'm going to tell you. On Schoology, like I said, you'll have some resources. It's one of those. So we're finding area. R dr d theta. Okay, so bounds for R, I'm going to start here and go out to the leaf. So it'll be 0 to cosine of 2 theta. If I'm choosing this leaf, what is the lower bound for theta? Yeah, negative pi over 4. We're going from here to here. So negative pi over 4 to positive pi over 4. Okay, this one you can't split up into 2 integrals. You're going to have to integrate with respect to r and then integrate with respect to theta. I'm going to do half of the problem just to show you something. So if we integrate with respect to r, we have 1/2 r squared from r equals 0 to r equals cosine of 2 theta. If I pull out the 1/2, I end up with the integral of cosine squared of 2 theta. Sorry. How do we integrate cosine squared of 2 theta? Without using a calculator, because I'm not going to let you use a calculator on your next test. You're going to use a trig substitution. Cosine squared of 2 theta. Okay, you could do 1 minus sine squared of 2 theta. Does that help us at all? No. Okay. Good thought, but no. Oh yeah, that one. Okay, there's a similar one for sine squared. If it was sine squared, it would be 1/2 1 minus. From there, you're going to integrate. I'm not going to. It ends up being pi over 8. Yes?
Why can't you split it up on this one, but you could on the other one?
Because of this upper bound being in terms of theta.
Oh, okay. Oh, all right.
Okay. Are we ready for one more? Great. Last example. We are going to find the volume of the solid. That lies under z equals x squared plus y squared, above the xy plane, and inside x squared plus y squared equals 2x. Okay. So, volume is going to be the double integral. It's always the upper surface. So in this case, this is our upper surface. So it'll be x squared plus y squared dA over the region R. We continue to see x squared plus y squared, which indicates to us that maybe polar might be best. That x squared plus y squared turns into an r squared. We then have r dr d theta. Okay. Forgot to ask us what these would be. Z equals x squared plus y squared. If I graphed that, what would it look like? Paraboloid. So that one's a paraboloid. What about x squared plus y squared equals 2x? That one would be a cylinder, yes. Okay, so we have to figure out what our region R is. So if you could picture, we have this paraboloid. We're looking for the volume underneath it, so that's where the paraboloid goes. The paraboloid, though, it has to be inside this cylinder. So that cylinder is going to be what defines our region R. With me so far? Okay, so take that cylinder. Specifically, we're interested in the circle that it makes with the xy plane. So we are interested where this intersects with the xy plane, because that circle will be our region R. If you complete the square here, you end up with x minus 1 squared plus y squared equals 1. So sketching that. That's our region R. Okay, that's going to help us find our bounds. Bounds for theta. It's not going to be 0 to 2 pi, because 0 to 2 pi would mean we were in all 4 quadrants. What's the upper bound for theta? Upper bound for theta. What is theta right here? Pi over 2. What's theta here? Negative pi over 2. So those are our bounds for theta. For R, R starts at 0, and it goes then to the circle. So we're going to have to put that circle in terms of R. If we start up here, we get R squared equals 2r cosine theta. Dividing by r, we get r equals 2 cosine theta. So that's the equation for the circle. That then will be our upper bound for r. Okay. Questions? Okay. Like I said,